And so we've talked about levers and wheels and gears. We've talked about inclined planes and screws. Uh, we'll talk about pulleys next. Now, imagine you have a 100-kilogram object on a rope. Uh, the force of gravity acting down on this is going to be 980 newtons. And if you want to keep that in place or move it upward at a constant velocity, you've also got to apply a tension to this rope of 980 newtons. Now, if you want to move this weight 30 meters upward, what have you got to do? You've got to take up 30 meters of rope in order to do that. Now, pulling 30 meters of rope straight up might be kind of difficult, and so we may introduce a pulley which would not change the amount of force we're applying, nor would it change the amount of rope we're pulling, but it would change the direction. So again, this 100-kilogram mass would be subject to force due to gravity of 980 newtons. And in order to keep it steady or move it up or down at a constant velocity, we'd have to apply a tension force to the rope of 980 newtons. Now, in this scenario where we have a couple of different pulleys, this is a different case. If we look at the 100-kilogram mass this time, there's still a downward force of 980 newtons. But the way we set up the ropes is such that, look, there are two lines, each with its own tension, supporting this 100-kilogram mass. And because there are two lines, the tensions on those two lines are going to be half of what they were before. And because the tension on this one rope, this is the one we're pulling on, is much less, that means we can pull with much less force. So whereas before we were pulling with a force of 980 newtons, here in this case, because the pulleys are set up so that there are two ropes supporting the mass, we only have to pull with 490 newtons of tension. If we look at the supports here and here, in this case, there's only 480 newtons of tension pulling on this support. On this support, there's 490 newtons of tension here, as well as 490 newtons over here also pulling down. And so there's a total force of 980 newtons acting on the support for this pulley. And this becomes important if the fasteners, which hold this to the ceiling in this case, are not strong enough to do that. Now in this arrangement, because we've halved our input force relative to our output force, because we've done that, we'll also have to double our input distance. When we halve the input force, we have to double the input distance. And so if you want to raise this by 30 meters, you've got to shorten this rope by 30 meters, you've got to shorten this rope by 30 meters, which means you have to pull 30 plus 30, or 60 meters of rope in order to raise this mass by 30 meters. Again, this is a trade-off. We don't have to pull as hard, but we do have to pull twice as far. And so these setups are called block and tackle. You can put in more pulleys, and every time you add a pulley, if you add it in the right way, then there'll be more ropes supporting the load, and that will reduce the load that you have to lift. However, if they're real pulleys and not theoretical ones, each pulley is going to add some friction, and you'll end up at a point where adding one more rope does not change the pulling force very much, but the friction of adding that pulley actually increases your pulling force about the same amount, and you've reached an impasse where you've gotten about as much mechanical advantage out of the system as you can. And so the IMA of a block and tackle system is going to be related then to the number of ropes that are supporting a weight. In this case, there are 2 ropes supporting the weight, and so P, or the pulling force, is going to be equal to half, or 1 over 2, 1 over 2 times the weight. In this situation, there are 1, 2, 3 ropes supporting the weight, and thus P, the pulling force, is going to be 1/3 of the weight. And so to find the IMA of a block and tackle system, we look at the number of ropes supporting the weight, and then the IMA is going to be that. It'll be equal to the number of ropes. And so you might imagine a pulley, another pulley up here, that's just used to turn the direction, to change the direction of that last string. Now, if you do that, it might look like there are 1, 2, 3, 4 ropes supporting the weight, but this one doesn't count because this does not add another supporting rope. It's just a continuation of this supporting rope. See, this rope here does not actually support the weight in any way. And with that information, we can try and determine the IMA for this system of pulleys. In this case, this would have to be a double pulley, a duplex pulley, so one pulley behind the other. This rope would go in, around the first pulley, up to the ceiling, back down, around the second one, and out. Now, if we want to calculate the IMA for the system of pulleys, we'd have to count the number of ropes that are supporting the weight. Here's 1, 2, 3, 4 ropes supporting the weight. Does this one count? In fact, it doesn't, because this is just a continuation of this 4th rope. And so our IMA is going to equal 4 for this system. And again, in a pulley system, just like anything else, in order to calculate AMA, we need to actually measure the forces with which we're pulling and the force that is being put out of the system, which is going to be equal in these examples to the force due to gravity acting on the load. And so AMA is, just like always, F out over F in. It's also going to equal then the force due to gravity on the load divided by the tension force on the first rope that you're pulling on. There are some textbook questions to deal with from this lecture on page 99 in the Shams book, 7, 10, 11, 12, 13, 15, and 16. Because this week's lecture was via video, Wednesday's class can be spent dealing with these questions. So my recommendation is that you try these questions, watch the video, try the questions, and come to Wednesday's class to deal with any problems that you might have. All right, thank you very much.